All right, let's talk about continuity. And we're going to start off this lesson on continuity by talking about continuity to the point. We will talk about what a continuous function means and what continuity in the context of an entire function means a little bit later. But for right now, we're going to talk about continuity at a point and different types of discontinuities by the end of this video. All right, so you might pause the video right now and copy down this graph because we're going to do some analysis on this graph. So hopefully you paused and copied down the graph, and let's talk briefly about continuity just graphically, just looking at it, and then we'll talk about more of a formal definition to figure out what do we mean when we say something is discontinuous at a point. So in this graph, we have clear discontinuities. I think if I said, hey, where is this graph discontinuous? You would probably say, well, it looks like it's discontinuous at 1, and it's discontinuous at 2. You can see there's breaks in the graph. Here we have a jump. The function jumps from 0 to 1, and here we have a hole in the graph. And I should also point out that this function is a couple of things. One, it's a completely legitimate function. It passes the vertical line test. And also, it's a piecewise defined function. So we could write this in function notation. It would have to be piecewise defined, right? So we look at the graph. We see that it looks discontinuous at 1, for example. But how do we know it's discontinuous? In fact, so what do we mean when we say that something is discontinuous? And what we mean is that the function value is equal to the limit at that point. So the function value at a point is the same as the limit value at that point. And to check whether something is continuous, you can either run that definition in your mind, but I teach what's called what I call the 3-prong test for continuity at a point. So I want to show you what those are. If the point that you're analyzing breaks any of the 3 prongs, then the function is not continuous at that value. All right. So 3-prong test for continuity at a point. X equals c, so x equals some value. X equals 2, -3, 17, something like that, okay? Prong number 1, f of c is defined. All right, so f of c has to be defined. Prong number 2, the limit as x approaches c of the function exists. Okay, so the limit has to exist. And then the third prong is that those two things are equal to each other. So we can write this: the limit as x approaches c of f of x is equal to f of c. All right, and if those 3 things are true, then we can say the function is continuous at a point. So let's analyze these 3 values, and we'll maybe do another one as well afterwards, but let's look at x equals 1, x equals 2, x equals 3 using the 3-prong test and see if the function is continuous or not there, right? So x equals 1, we look at x equals 1 and we check. Prong number 1, it is, does the function exist there? Yes, it does. The function exists at 1, its value is 1. Okay, so f of 1 is 1. So that's good. Prong number 2, does the limit exist? No, it does not. The limit exists if the left and the right-hand limit approach the same value or equal the same value. From the right, we see that the function is approaching 1. From the left, the function is approaching 0. Those are different numbers. So the limit doesn't exist. So at x equals 1, it's discontinuous. Because the limit as x approaches 1 of f of x does not exist. Okay. All right, let's go check x equals 2 then. At x equals 2, we check, does the function exist? Yes, it does. It exists right here. Does the limit exist? Yes, it does. From the left and the right, the limit is equal to 1. Okay, so the limit as x approaches 2 of the function is 1. Are they the same thing? No, they're not. Breaks the last prong of the 3. The limit and the function, while they both exist, are not equal. So this one is discontinuous. because the limit as x approaches c of f of x does not equal f of c. In fact, we should use the actual numbers. So limit as x approaches 2 of the function does not equal f of 2. Okay, so it's discontinuous there. We check x equals 3. Now x equals 3, again, graphically, you look at this and you think, seems continuous. There's no break in the graph right there, and you'd be right. The function value is of 3 is 2, the limit exists, and the limit value is 2. They're the same, so yes, it is continuous at x equals 3. So that's how we checked for continuity at an interior point. I didn't say that at the beginning, but we're checking the interior points here, so inside of this interval, because this function only exists from 0 to 4, all right? What about at an endpoint? So let's check and see, is this function continuous at 0? So let's check x equals 0. To check continuity at an endpoint, the three-prong test still applies, but we check either a right-hand limit or a left-hand limit, okay? So here, we still check to see if the function exists, and then we check and see if the limit, we check either the left or the right-hand limit, all right? So if we want to check at x equals 0, we check, does f of 0 exist? Well, yeah, it does. F of 0 is 1. Okay, so that's prong number 1. Prong number 2, does the limit as x approaches 0 from the right, so from the positive side of the function, does that exist? Let me check. Yes, it does. Okay, so if we're checking a left endpoint, we check the right-hand limit. When we're checking a right endpoint, we check the left-hand limit. That's the only difference. Okay, so this does exist and it equals 1. And 3, f of 0 is equal to 1, which is equal to, f of 0 is equal to the limit as x approaches 0 from the right. All of that's equal to 1. So it does exist at an endpoint. It is continuous at the endpoint. Okay? And that's, again, the formal definition works there. It's just a left or right hand limit. All right, so that covers all of those things. Let's talk about the different types of discontinuities, and then we'll call it good for this video. All right, so leave that for now, I guess. Different types of discontinuities. Okay, so we have removable discontinuity. Okay, so that could look, so we have some arbitrary function here. There's usually a removable discontinuity is denoted by an open dot. All right, and so it could be something like that. It could also be something where there's an open dot and the function exists, but it's not wherever that dot is, like we just saw in the example that I had up on the board just a minute ago. Okay? So that's removable discontinuity. We have jump discontinuities. A jump discontinuity is what you might expect. The function jumps. Okay, so you're going along, everything seems fine, and then it jumps either up or down. Okay, so we have a jump discontinuity. I don't really need this anymore. Then we have an infinite discontinuity. All right, and an infinite discontinuity is just a vertical asymptote. So that is a very bad y-axis. All right, so maybe we have a vertical asymptote, and maybe it's one of these volcano graphs, one of my favorites. Okay, so something like that. Okay, but an infinite discontinuity is just it's just a vertical asymptote. Okay, the last type, which is easily forgotten, is called an oscillating discontinuity. I think that's spelled right. At least that's what I wrote down in my notes. An example of this would be something like sine of 1 over x. And you might take a second now and in Desmos or in your graphing calculator, graph sine of 1 over x and see what happens. It's something like this. I'm not going to be able to sketch it in a fantastic way, but it looks something like this. So it comes in like this, and then the closer you get to the y-axis, the more it oscillates, the faster it oscillates. All right, and then on the other side, it crosses the x-axis slower as you move to the right or to the left on it. But yeah, so as you get closer to the axis, the function just oscillates faster and faster. And you can see that if you plug in 0, you get a divide by 0 error, but it's not a vertical asymptote. This is called an oscillating discontinuity because it's not continuous at 0. But you can see that it's sort of fundamentally different than a vertical asymptote, a jump, or a hole in the graph. So that's it for the different types of discontinuities. One last thing I'll say that you may want to write down, although I don't think it's earth-shattering or crazy to sort of comprehend if you've understood everything to this point, but if we say something is continuous on an interval, that means that it's continuous at every point on the interval. That's what we mean by continuity on an interval. In the next video, we'll talk about what we mean by a continuous function. That's something slightly different, but continuous on an interval just means it's continuous at every point in the interval. And that's it for the beginning of continuity.